As you drill for oil, deeper and deeper, you're drilling into some real contamination, and it affects your mud condition. Testing the mud is the first line of defense in predicting impending troubles. In Part 2, we went over some of the contamination problems you'll have with mud and how they can be corrected. But detecting these problems is the key element in a successful mud program. To catch problems before they get too serious. That's what we're going to look at next. How are these tests performed, and what do they tell you and the mud engineer? Changes in the mud characteristics are what we're looking for, and to find them, a whole array of tests are performed. It starts with your two basic tests, mud weight and viscosity. We'll start with mud weight. When we talk about mud weight, we're really referring to mud density. Mud weight is usually taken every 15 to 30 minutes to help the driller and mud engineer determine whether or not the weight is remaining consistent. The intervals of checking might change according to the activities on the drill floor. Mud weight changes can be caused by salt water or freshwater flows into the mud, changing the solids to liquid ratio. Or it can be due to faulty cleaning equipment leaving too many drilled solids in the mud. Or maybe your driller has drilled into a formation that's adding fine particles to the mud that can't be removed by the solids control equipment. Or it could be something as simple as the drill floor crew washing down the pipe and the floor with too much water and diluting the mud. Another common problem is somebody washing down the shaker screens, like this. This can add too much water to the system. Whatever the reason for changes, the mud weight is important, so your tests have to be done regularly and accurately. And both you and the mud engineer will be taking the weights. So naturally, a scale is needed, and you've probably already been introduced to a mud balance of some sort by now. But I'll bet you didn't know that every week or so you should check it for accuracy.
In using the standard mud balance, 3 points should be made. First, the lid. The lid received with the mud balance should be one that's always used with the mud balance. It's a calibrated instrument, and the changing of this lid could alter the reading of the drilling mud. Secondly, the calibration. Water weighs 8.3 pounds per gallon. Calibrate the instrument by placing water into the bowl. Water, when balanced, should split the hair that is shown on the balance bubble. If it is out of calibration, it can be calibrated by either adding or removing lead shot found on the end of the scale. The third point that one should make out is when weighing the mud, it is important that you weigh it dry. If you weigh the mud with only a wet bowl, a difference in the reading of the mud will be obtained.
When checking the scales, be sure you use distilled water because it always weighs 8.33 pounds per gallon and can be used as a worldwide standard. Place the lid on top and dry it off. Be sure to put a finger over this hole. Then place the balance arm over the fulcrum. Slide the counterbalance until you get the bubble centered in the level gauge. Your scale should read 8.33 pounds per gallon or 62.3 pounds per cubic foot. If it's not exactly right, you can make mathematical adjustments pretty easily. For example, if the reading is heavy by 0.1 ppg, subtract 0.1 from the reading of your mud density. Better yet, fix the scale. This is done differently on the different scales, but on this IMCO, it's done by adding and subtracting these little rubber O-rings from the end of the balance. On the Baroid, it's done by adding or subtracting shot at the end. Once you've got this done, you'll know your readings will always be right unless you don't weigh it right. Maybe we'd better go over that procedure too. Take a mud sample from the return tank. Be sure that for each reading, your sample comes from the same place. Fill the cup to overflowing. Dip the lid into the mud sample and spin it onto the cup. This seats it to make sure all air is out of the cup. Cover up the hole in the lid and rinse the mud off of the cup. Then dry it. Place the balance on the fulcrum. The knife edge fits into the grooved top section of the base on this particular unit. Slide the counterbalance until the bubble in the balance glass is centered. The density of the mud sample is read at the edge of the sliding weight nearest the base support. There will usually be 3 or 4 scales etched or imprinted into the balance arm. The ones you'll be concerned with are pounds per gallon, pounds per cubic foot, kilograms per cubic meter. Mud weight should be logged into the mud weight column of your mud logs, along with the time of day that they were taken, and log in the mud temperature too. Next is viscosity. Now, the test you take that's called a viscosity test really doesn't tell you what the viscosity is. It'll just tell you when there's a change in the viscosity. The mud engineer will run a test that we'll go over a little later that'll give him an exact viscosity. Your test is made with this funny-looking funnel called a Marsh funnel. It's 6 inches in diameter at the top and 12 inches long. Down here at the bottom, you have a 2-inch neck with a 3/16 of an inch hole in it. There's a wire mesh screen up here on top that's used to strain larger particles out of the mud sample so it doesn't plug up your 3/16 of an inch hole. Just like with your mud balance, you ought to check the accuracy of your funnel every now and then, or every time you start to use a new funnel, or one you haven't used before. It's done with fresh water between 65 and 75 degrees Fahrenheit. It should take 26 seconds to fill a 1-quart beaker. If it's not within half a second of this, you'll need to figure out why. If it's too slow, it's probably because the funnel is plugged. A 3/16 inch drill bit will correct that. If it's too fast, the hole's too big, you'll need to get a new funnel. Now let's measure some mud. Put your fingers over the hole and fill the funnel up to the screen. Make sure the mud is strained through the screen. Now, drain the mud into your cup or a beaker that has a 1-quart line. Time the flow from the time you first start it until it reaches the 1-quart line. Then enter the time into the logs. You'll need to log in the temperature of the mud too, since this will affect viscosity. Always be sure to clean your equipment up after using it. You remember a few minutes ago I said that this test isn't very accurate? Well, let's take a look at how the mud engineer gets an accurate viscosity reading. He starts with a sample of mud that is delivered by you. You know, earlier we told you that you should always take your samples from the exact same place. Well, the mud engineer needs the same thing for all his tests. And he'll need it to be in his cabin for testing within 5 minutes so that his readings reflect the qualities of the mud at the drilling temperatures. So keep this in mind. When he measures viscosity, he uses a fan VG meter, and he's really measuring several different things: plastic viscosity, yield point, and gel strength. These terms probably don't mean much to you right off, so let's talk about what they are exactly. We'll start with plastic viscosity. The dictionary definition for plastic viscosity is a fluid's internal resistance to flow due to mechanical friction between individual solid particles. What this really means is that plastic viscosity is the measurement of the ability of a liquid, in this case mud, to flow. It's sort of like diving into water. A diver just sort of falls through the air, but when she hits water, there's a lot of resistance between the water and her body. It really slows her down. And if the water were saturated with something like mud, it would slow her down even more because of the nature of the liquid. The friction between her body and the molecular particles that make up water resist her movements. The more particles that are packed into a given area, the more resistance, which causes the motion to be even harder to maintain. This resistance is measured by the fan VG meter. Here's how it works. There's a solid cylinder that's attached to a needle or scale. A spring brings it to a zero position. Another cylinder is placed around the first one. There's not a lot of space between them. This outer cylinder is turned either by a crank or a motor. As it turns, it doesn't touch the inside cylinder, but whatever liquid is in between the cylinders begins to turn along with the outer one. But the inner one is trying to hold the liquid still. So, by reading the scale attached to the inner cylinder, we can tell how much resistance the liquid has to the motion of the outside cylinder. The cylinder is turned at 600 RPM, then at 300 RPM. The 300 RPM reading is subtracted from the 600 RPM reading to get the plastic viscosity, which is recorded in centipoise. Readings are entered into the drilling mud report. Here's an example. If your 600 RPM reading is 92 and your 300 RPM reading is 52, then your plastic viscosity, your PV, is 40. You can see that this measurement is a lot more scientific than your Marsh funnel. Keep in mind that this measurement is strictly a resistance to flow caused by mechanical friction, particles bumping against each other. There's more to viscosity than that. There's also a factor called yield point. This is the fluid's resistance to flow as a result of electrical attraction. Many muds have a feature that aids in maintaining viscosity by particles pulling together like microscopic magnets. They try to join together as they come near one another. It's not just a resistance caused by friction of particles. It's resistance caused by the electrical attraction of the mud particles to one another. Yield point is measured in pounds per 100 square feet, and it's figured mathematically from the figure you got for plastic viscosity. Subtract the plastic viscosity, which is 40, from the 300 RPM reading, 52. This gives you a yield point of 12. The last feature that's measured with the fan VG meter is called gel strength, or shear rate. Gel strength is a measurement of the mud's ability to hold cuttings when it's at rest. The same electrical attraction that results in yield point causes gel strength, except when it's not in motion. Your gel strength should be high enough to stop cuttings from falling to the bottom when pumping has been stopped for a connection or a trip. But it's got to be low enough to let the driller get flow started again without putting too much pump pressure against the bottom of the hole, which could cause damage to the formation and even cause you to lose circulation. In order to figure out the gel strength, two tests have to be made. The mud should be stirred up by turning the fan VG meter on 600 or higher RPM for 10 to 15 seconds. Then let it set for 10 seconds. The engineer will rotate the meter very slowly at about 3 RPM to see what force it takes to make the mud let loose of the inner cylinder. Watch. The needle will start to move, then fall back almost to zero. This highest reading is what he's looking for. Now he'll stir the mud at 600 RPM again for 10 to 15 seconds. Then he'll let it stand for 10 minutes. Then he'll take another 3 RPM reading. Again, when the needle drops back to a lower number, the gel strength has broken. This is called the 10-minute gel strength test. These figures are logged into the form. They tell the mud engineer how quickly and to what degree the mud is gelling. They'll help him determine whether or not the mud qualities are consistent with what the conditions require. It'll also let him know if he has contamination problems. The next test he'll probably do is called the fluid loss test. It's a test that'll give him an idea as to how much fluid is lost before a permeable formation is sealed and how much of a filter cake builds up. The idea is that a sample of mud is put in a pressurized container that has a 9-centimeter filter in it. Under a pressure of 100 pounds per square inch, the mud is strained for 30 minutes. Before too long, the mud particles are going to try to clog the filter paper and slow the flow of liquid that's squeezing through. The amount of filtrate, or filtered liquid, is measured and recorded. Then the lid is unscrewed and the filter paper is removed. This is the filter cake. Here, it's the thickness of the mud layer that got deposited on the paper after 30 minutes. This is recorded too. These two observations tell the mud engineer what wall building characteristics the mud has. After all, the filter cake is sort of a temporary liner until steel liner can be run. You certainly don't want it leaking or soft and mushy. The filtrate and mud are tested for their content of lime, chloride, calcium, magnesium, and other things.
We use .02 normal sulfuric acid and titrate the red color back to its original state.
These tests are made by using chemicals and a system known as titration tests. They're all done with chemicals and are measured by their chemical reactions. The mud is also tested for its pH level with pH paper.
At this point, I check the pH, and on this mud at this range, I'm trying to keep it between 9.0 and 9.5. I came up with a 9.0.
This pH meter is used sometimes instead of pH paper. pH affects the mud's ability to dissolve additives. Low pH mud also corrodes pipe and interferes with the viscosity control of bentonite. Caustics are added to the mud system to control the pH level. It should usually be about 9 to 10.5. Another test he'll do is a sand content test. Basically, this test just tells him how much sand is being retained in the mud.
I'll pour a quantity of mud into the sand content tube up to a line where it says mud. Now we'll fill it up to the water line. And now we'll mix the mud thoroughly by shaking it. We'll run it through our screening device. Now let the mud filter out, leaving the sand. Now I'll put it on a small funnel, put it back on my glass tube, and run more water through it.
Sand is harmful to all moving parts in the system, especially the mud pumps, so this has to be watched carefully.
Now we'll read the sand content, which it's marked from 0.25% all the way up to 20%. And in our sand on this location, we're showing 0.25% sand in our mud, which is a very acceptable level.
Finally, the mud engineer might run a retort test to determine oil to water content and solids concentration of the mud.
We're going to put approximately 20 cc's of mud into this cylinder.
What this test does, essentially, is to take a sample of mud and boil off the liquids.
This is one test that should be ran daily. Now we'll plug it into our power source. Put it into the unit. As you can see, she's beginning to cook off already. And we'll have our water content on the bottom. If there's any oil in the mud at all, it will show up on the top part of the water, which we should have somewhere in the neighborhood 4 to 5% solids in the mud, which that'll be the void spot at the top. That'll be our undesirable solids that our mechanical equipment has not taken out of the mud.
The liquids are measured in a graduated flask after all of the condensation stops, usually about 30 to 45 minutes. The solids remain in the container. Once the mud engineer's run all his tests, he'll have a pretty good idea as to what's going on with the mud downhole, and he'll be asking you to make adjustments in the mud from time to time. One final thing that is sort of a last resort, the mud engineer will probably have one of these kits. It's just a cabinet that contains samples of all the mud additives. If he runs into a problem that he can't figure out by using his tests, he'll start experimenting with a little of this and a lot of that until he finds a cure. So you might get into quite a few exotic additives from time to time.
that's about it for part 3 now. In our next part, we'll talk about the mixing equipment and how to mix the mud and additives safely.